Hey guys, thanks for watching. I just wanted to make a quick video about trees. So you're going to be seeing trees in next week's lectures and labs, and you're going to be using trees in assignment 3. And I just wanted to make it a little bit less daunting for you, because the truth is that you've actually been using trees for a while, a few weeks. And the only things that you really need to know are what trees actually are, how you've been using them, and how to change the structure of the trees that you've been using. So first I'll tell you what a tree is. So a tree is a data structure. And you might be thinking, what's a data structure? Well, a data structure is a way of representing data. So I've got a picture of a tree up on the screen here. So this first circle is called a node, and each node stores a bit of information. And each node also has a number of branches leading to other nodes, and each of the branches is pointing downwards, and that is an important concept because it's kind of like moving through the tree, moving away from the original node, also called the root node. So here we have the root node, and this will contain a bit of information. Maybe it'll contain a number or a word or something. And then we have the option to travel down the left branch or the right branch to get to the next node, which will also contain a bit of information. And this will continue until you get to the end of the tree. And the end of the tree is called a leaf. It's not called a node. And leaves generally don't have any information in them. They just signal that that's the end. There's no more nodes, no more information. And something cool about trees is that if you look at each subsequent node from the root node, they're also called children nodes, child nodes. If you're moving down the tree, it's called a child node. If you're moving up the tree, it's called a parent node. So if you look at each of these child nodes of the root node, they are actually trees themselves. We could actually just get rid of this and get rid of these branches, and then we would have two complete independent trees here. Okay, so hopefully that gives you a bit of an idea of what trees are. It's just a way of structuring data. And now I can talk to you a little bit about how you've actually already been using trees. But first of all, I need to mention something called a branching factor. So a branching factor, when you're looking at trees, is how many children each node has. So this node is called a binary tree, and it's called a binary tree because each node has two children, exactly two. So even if it wasn't nice and neat like this, and this part of the tree was missing, for example, this node would still have two children. It's just that this child would be a node and this child would be a leaf. So in a binary tree, you've always got two children. But it doesn't have to be two. It can be 3, it can be more, and it can be less. And that brings me to talking about lists. So lists are actually just trees that have a branching factor of 1. So each element is its own element with its own bit of information, and it contains a pathway to the rest of the list. And so if we can just kind of like look at this leftmost branch here and pretend that the rest of the tree doesn't exist, it actually just looks like a list. So here's the first element of the list, here's the head of the list, and then here's the tail of the list. And then once you've done something with the head, you move on to the next element, and suddenly this becomes the head of the list, and this is the tail of the list. And when the list ends, instead of it being a leaf, it's the empty list. So this would be the open square bracket, closed square bracket with nothing in between, and these would be all of the elements. I can demonstrate that now. So if we have example, we can put a bunch of elements inside a list. And we all know what this looks like. This is the first element, and here's a constructor indicating that you're joining one element to the rest of a list. And here's another element, and here is finally the end of the list, which is the empty list. So I've just got here the standard definition of lists and the custom definition of lists, which you guys worked with a few weeks ago. And what I've done here is I've just copied and pasted this custom definition of lists, except I've changed a few of the words. So instead of custom list, I've got tree. The A is still there. Instead of an empty list, I've changed that to leaf. Instead of cons, so cons would be the constructor of a non-empty list when you're dealing with this custom list type. So instead of that being the constructor, I've written node as the constructor. They both still contain an element of type A, and they both also contain another of the same data type. So this one is an element, and it's also the rest of a list of those same elements. And this is the same thing. This is a node. It has an element, A, and it also has the rest of a tree. Now at the moment, because these are identical in structure, it's just that the names have changed, what we're looking at here is a tree with a branching factor of 1, which is exactly the same as a list. So now I'm going to show you how to change that definition slightly to work with binary trees or more. So as many as much branching factor as you need. All you need to do is copy this and paste it. So what this is doing is it's saying, okay, something of type tree is still either going to be a leaf, which is exactly the same as an empty list, or it's going to be a node, and the node is going to contain a piece of information, which could be, an integer or a word or whatever it could be. It's also going to contain the rest of a tree, but it's going to contain that twice. So this will be the left child node, and this will be the right child node. And if we go back to the custom list definition, we can see that it's almost exactly the same. You've got empty here representing the end. You've got a constructor here representing something that's not the end. And that contains an element. And you can kind of look at this like it's a child node as well. It's the rest of the list. And since you're moving forward through the list, you can kind of consider it the child node. And it might be another list, or it might just be an empty list. And it's the exact same thing here. Yeah. So what that lets us do is it lets us work on this data structure called a tree in a very similar way that we would work on lists. So just to give you an example, the way that we can write a function that will find whether or not an element is in a list is actually really similar to the way that we'll do the same thing for a tree. So I'll just demonstrate by showing you the differences and the similarities. So here we're looking for whether there's an element in a list. So what we want is a list, and we need to make sure that we can use the equality operator on it. We also want an element, which is of the same type, hopefully. And then we want to output a Boolean value to indicate whether or not that element is in the list. Okay. Now we can just call the input value list, and then we'll call the element ln. And actually we're going to use guards for this. So we'll go down here and we'll say okay, before we use guards, we're going to use case matching, pattern matching. So we're going to go case ls of, and then it can either be an empty list, in which case the answer is false, or it can be a non-empty list, in which case we use guards. We check whether the element is equal to x, and if so, we return true, and if not, we keep searching the list. And instead of here, we want to use the tail of the list rather than the rest of the list. Okay, so let me just comment this line out. And I'll comment this out as well for now. Okay, so let's use this. Just check whether it works. So we want a list, and we want an element. Okay, so 5 is not an element of that list. About 3. Okay, so it seems to work based on those two examples. Now let's do the same thing but for a tree. So we want to make sure that what we're using is still equatable or equitable. I'm not sure which. So we want something that's of the form tree A this time. We also want an element of type A, and then we will return a Boolean. Okay, so let's name our tree tr, and we'll name the element ln, and then we'll use pattern matching again, case tr of. So here we're checking whether the tree is just a leaf or whether it's a node that contains information and also contains child nodes. So if it is a leaf, that's the base case. So let's check the base case. Case tr of leaf. If we just have a leaf, then the element is not an element of the tree. So we will say false. Now, what do we want to do for the next case? We know that we've covered the base case, which is leaf, just here. So the other case is this case. And that, if we're going to use the constructors here, which we do need to do, we can type node, and then this will be a second element, but we can just call it A because the name lm has already been taken, and then we can say left and right, and left and right will bind to the first child and the second child respectively. Okay, so once we've bound a name to each of those different elements of the node, we can use guards. So if lm is equal to A, then obviously the tree contains the element, because we're looking at a part of the tree. That part of the tree contains the value A, which is the same as the value that we're looking for. So that tree contains the value we're looking for. So we'll return true. Otherwise, now, in the first example, all we did was we moved on to the rest of the list. And it's the same concept. The only difference is that the rest of the tree is actually two trees, because this particular type of tree has a branching factor of 2, and each node will have 2 child nodes, as opposed to having 1 child node, which is the case when you're working with lists. So we go otherwise. We need to check whether it's an element of the left, and we want to use the same element, or check whether it's an element of the right. So this first part is exactly the same as this part. We're just moving on to the rest of the list. But if we just look at one of the child nodes, we're ignoring half the tree. So we want to look down both paths. We're checking the left tree and we're checking the right tree. And so this is recursive in the same way that this is recursive. You're going to check, if you have a node, that node is going to represent a tree. And that node is going to contain a piece of information. And that piece of information is either the piece of information that you're looking for, in which case you can return true, or you can continue to search through the tree. And searching through the tree means that you need to search both the left and the right. Okay. Now this might be a bit hard to understand, but I think it's a good idea to cover it a bit earlier. That way, when you're in the lecture and the labs, you can focus more on understanding specific things that you haven't been able to understand yet, rather than just trying to take it all in and not really knowing where it's coming from, how it's similar to what you've been doing before. Just one last thing to mention. I've put it like this to make it the same structure as the custom list that you've been used to, but it can actually be in any order. So we can put the A in the middle, or we can put the A at the end, just the same as with custom lists. We can put the A at the start, or we can put it at the end. We can't really put it in the middle because there's nothing to put it between. Not only that, but you can choose your branching factor. So you can choose how many children each node has. So at the moment we've got 2, but we can make it 3, we can make it 4, we can make it 5. Generally, at least at the start, you'll want to be working with 2 child nodes. There's a lot of advantages to working with just 2 that I won't go into at the moment, but in your assignment 3 you will probably be working with a few more, a little bit more than 2. And that's all that I really wanted to say. If you have any questions, you can ask on Piazza. So thank you again for watching, and just remember, if it doesn't all make sense, that's fine. You're going to have a few exposures to these concepts, and the important thing is that you try and pick up just a little bit each time. So thank you, and I will see you later.